the continuation of a set theory. In this lecture number 13, I am selected these things here: cardinality of sets, and thereafter the equivalent sets, denumerable and non-denumerable sets, and countable sets, and some related theorems and examples on these denumerable and countable sets. Let us mention cardinality of sets. The cardinality of set is the measure of the size of a set. The cardinality or cardinal number of a finite set is the number of elements in the set. Cardinality of, suppose the set A is denoted by A in the between two lines, read as length of A or magnitude of A or simply mod A. Mod A is the familiar thing to us. So totally what we mean by the cardinality of set? Cardinality means the length or size of a set, or it is the number of elements in the set is A called the cardinality of the set. Now to go for the cardinality of a finite and infinite set. If A is the finite set, then A is either empty, no element it containing, it is also called as the finite set, or A containing the particular elements 1, 2, 3 up to n. For every small n belongs to the natural number capital N. Then we can write the cardinality of A is n here. If A is infinite, then A may be containing the so many elements 1, 2, 3, 4 and so on. Then the mod of A in this case is a infinity. Equivalent sets. When the two sets are called as the equivalent. The two sets A and B are said to be equivalent if they have the same cardinality, symbolically denoted by A equivalent to B by means of a symbol. That variation line indicates the symbol of equivalent. Next, to go for the one note among the equivalent of two sets, if A is equivalent to B, then there must exist the bijection mapping from A to B. So it should be noted that if A is equivalent to B means there is a bijection mapping F from A to B. Next, the question arises, already you studied the equivalence relation. Whenever the relation is said to be equivalence, if it is a reflexive, symmetric and transitive, then the relation is called as the equivalence relation. Now the question arises, is equivalent sets form an equivalence relation? Definitely answer is yes. Why it is so? Equivalent sets form an equivalence relation. Clearly the A is equivalent to A. Therefore equivalent set is reflexive. And second, suppose A is equivalent to B, then immediately B is equivalent to A. Therefore equivalent set is symmetric. Now in the third case, if A is equivalent to B and B is equivalent to C, then immediately A is equivalent to C is obvious. Therefore equivalent set is transitive. Hence the conclusion, equivalent set form an equivalence relation. Thereafter we can go for the definition of a denumerable set. A set A is said to be denumerable if it is equivalent to n. What does n here? N is the set of the natural numbers. That is, A is equivalent to n. Other words, a set A is said to be denumerable if there exists a bijection F from n to A. If there exists a bijection from F from n to A. With the help of this denumerable set, to define a countable set. Whenever the set A is said to be countable, a set A is said to be countable set if it is finite or denumerable. Denumerable already defined. If it is finite or denumerable, it is obvious that every finite set is countable and every denumerable set is countable. Denumerable means n is equivalent to the set. Suppose any set, if it is equivalent to n, then you can say as the denumerable set. Now, what is uncountable set? A set A is said to be uncountable if it is finite or it is equivalent to n. Next, we go for the examples on this. Example for the countable set. The set of natural numbers is countable. And one more important example, it is not countable is given. The interval 0, 1 is uncountable. Consider some definitions of a countable, denumerable and numerable sets. To go further, some theorems on the particular things. The theorem here it is, prove that the set of all integers is countable. The set of all integers is countable. Go for the proof. Let the capital letter I denote the set of integers. The set of integers is the positive integers 0, 1, 2, 3, 4 and so on, and negative integers minus 1, minus 2, minus 3 and so on. The set of integers I said. Now to consider the set of natural numbers, those are the set containing the 1, 2, 3, 4 and so on to be the set of natural numbers. Obviously I is infinite set, n has infinite set, obviously I is equivalent to n, therefore I is denumerable since it is countable. Otherwise, to define the set of the natural number n to I, a mapping f from n to I by two-way f of n equal to the set of the elements of the type n minus 1 by 2 or minus n by 2. Whenever the n minus 1 by 2, the n is particularly odd number. When you get it in the minus n by 2, the n is particularly even number. With the help of this definition, f from n to I defined by f of n equal to n minus 1 by 2 n minus n by 2, to show that f is a bijective. That means to show that f is both on one and on two. To go for the proof of this f is both on one and on two, in the first case, to consider if n is odd. If n is odd means f from n to I is defined by f of n equal to n minus 1 by 2. I will say this is 1 mapping because as consider f of x1 equal to f of x2, as per the definition it becomes x1 minus by 2 is equal to x2 minus 1 by 2. Immediately both the denominator 2 cancels, minus 1 minus 1 cancels, we left x1 equal to x2. What is the conclusion? F of x1 equal to f of x2 implies that x1 equal to f2, therefore the mapping f from n to I is 1, 1. Similarly, to show that this mapping is onto, for that I consider the y belongs to an integer, then there should be exist another number x, 2y plus 1, such that f of x is written as a 2y plus 1, then immediately this n has been replaced as a 2y plus 1, that is 2y plus 1 minus 1 divided by 2, minus 1 and minus 1, 2y divided by 2, 2 cancels, we left f of y, that we get f of x equal to y. We get f of x is equal to y, therefore if f of x equal to y for every y belongs to I and x belongs to n, then the mapping is a onto. In this case, f is both on one and onto, therefore we can say that f is bijective, hence n is equivalent to I, therefore I is countable. Next, go for the, in case of n is odd, it is defined that f of n equal to minus n by 2, to show that this is a 1, 1 and onto. Again I taken the f of x1 equal to f of x2, so immediately this is minus x1 by 2 is equal to minus x2 by 2, we get x1 equal to x2, therefore conclusion is f is 1, 1. Similarly, let y belongs to I can be taken, then there is the element x equal to minus 2y, such that f of x equal to minus of minus 2y divided by 2 is only y, not f of y, it is only y. Therefore f of x equal to y, therefore f is onto. In this case f is bijective, hence the n is equivalent to I, therefore the I is countable. So this is the thing. Another one, prove that every infinite set has a countable subset. Every infinite set has a countable subset. For that I take the, let S be an infinite set. Let A1 belongs to S, then S may not be equal to A1 because S is infinite, it containing more than the some elements. Let A1 and A2 belongs to S, then S is not maybe A1, A2 because again S is infinite. Continuing the process, we get a one proper subset A of S, that A containing the elements A1, A2, A3 and so on to be up to infinite elements. Now to define a function f from n to a by f of n equal to an for every n be the natural number. No doubt that f of a1 equal to f of a2 implies a1 equal to 1, that f of a1 equal to f of a2 implies a1 equal to a2, therefore f is 1. Now for every an belongs to a, there exists n belongs to n, and it is such that by definition f of n equal to an, therefore this f is onto. That means the mapping f from n to a, what you defined, it is both 1 1 and onto, therefore f is bijective, hence n is equivalent to a, therefore a is countable. This a is nothing but a subset of an infinite set S, therefore the conclusion is every infinite set has a countable subset. Next, go for another theorem, prove that the set of natural number n is countable. Or, in other words, prove that the set of positive integers is countable. For that, you have to consider a mapping f from n to itself, n. Defined by every n belongs to n, there is a n belongs to n. Therefore, f of n equal to n has been defined. It is 1 1, and even though it is onto, because for every y belongs to n, there exists x belongs to n, such that f of x equal to y. Therefore, f is onto. Our conclusion is f is 1 1 and onto, hence bijective. Therefore, the f from n to n is equivalent, bijective, and n is equivalent to n. Therefore, immediately n is bijective, or n is countable. Next, go for the another theorem. Prove that the set n cross n is countable, where n is the set of natural numbers. Prove that the Cartesian product of countable sets is countable. In other words, let n be the set of natural numbers. To prove that n cross n is countable, that is n is the set of the numbers containing the 1, 2, 3, 4 and so on. I will take the a1 is the set containing the pair 1, 1, 1, 2, 1, 3, 1, 4. That means 1 is fixed in the first element. 1, 2, 3 has been changing in the second element. That is the A1 I formed. 1, 1, 1, 2, 1, 3, 1, 4. Similarly, the A2 I can go for. The 1, 2, 3, 4 has been fixed in the second place. And 2 can be taken in the first place. 2, 1, 2, 2, 2, 3, 2, 4. Similarly, the A3, 3, 1, 3, 2, 3, 3, 3, 4. In this way, I continue the process. From the set, the n cross n has been immediately formed, the set containing A1, A2, A3 and so on. It is the Cartesian product of the two sets. Now our idea is to show that this is countable. It is obvious that this n cross n containing the infinite brackets, and n is also the infinite brackets, infinite terms. Therefore, this n cross n is equivalent to n, and n is denumerable. Therefore, n cross n is denumerable. Nothing but n cross n is a countable set. So, this is the proof of n cross n is countable. Next, go for the theorem, prove that every subset of a countable set is countable, or prove that a subset of a denumerable set is either finite or denumerable. Prove that every subset of a countable set is countable. First, you can take the one countable set, and the subset A is the subset of S. Let S be the countable set and A be the subset of S. Our idea is to prove that A is countable. Since S is countable, means either finite or denumerable. If S is finite, first case I taken, if S is finite, by definition every finite set is countable, and A is subset of S means A is also finite, therefore A is also countable. Case 2, if S is denumerable, that means infinite, then immediately S is equivalent to N. If S is equivalent to N and S containing the number of infinite elements A1, A2, A3 and so on to be, and A is subset of this S. A is subset of this S, where A may be either finite or infinite. If A is finite, it is countable. If A is infinite, then A containing the elements you can say AK1, AK2, AK3 and so on. Now, to define a f from n to a by f of n equal to a and k, this mapping is both 1 and onto, we can say bijective. Therefore, a is denumerable, hence it is countable. So it is the proof that every subset of a countable set is countable. Now to go further, prove that the set of rational numbers is countable. Rational numbers means Q, that Q containing the positive rational numbers, negative rational numbers, and including 0. Totally it is the rational number. First we consider Q plus is countable. For that we have to construct the Q in the form of A1, A2 and so on. The A1 is the set containing 1 by 1, 2 by 1, 3 by 1, 4 by 1. The 1 has been replaced in the denominator to try to be A2, and continuing this by means of 1 by 3, 2 by 3, 3 by 3, 4 by 3. The so on element has been continued. Lastly, the an I will take 1 by n, 2 by n, 3 by n, 4 by n and so on. The process so to be concluded. This is nothing but the Q plus. This Q plus means the set containing A1, A2, A3 and An. Clearly this Q plus is equivalent to n. Therefore Q plus is denumerable. Hence it is countable. If Q plus is countable means the negative rational numbers also countable, and 0 is finite set, it is always countable. Hence Q is the set of rational number, it is always countable. Next to go for the proof of the another theorem, prove that union of two denumerable set is again denumerable. Let A and consider the proof, let A and B be the denumerable sets. Our idea is to prove that A union B is also denumerable. A is denumerable means it containing the infinite set. I taken that let A equal to A1, A2, A3, An and so on to be. And again B is the denumerable means I will consider that B equal to B1, B2, B3 and Bn and so on to be. Now to define F from n to A union B by F of n is equal to either An when n is even or Bn when n is odd. So it containing F of An both the An and Bn terms, therefore F is 1 1 and therefore A union B is denumerable. It is the proof of the theorem union of two denumerable set is denumerable. Similarly, prove that the union of two countable set is again a countable. Here the one thing will be extra happens because of finite. Countable means finite or denumerable. Denumerable is denumerable shown already. Now consider the proof. Let A and B be the countable sets. To prove A union B is countable, suppose A and B are finite set. Case 1, let A and B are finite set. Immediately A union B is also finite and every finite set is countable. Therefore, the conclusion A union B is countable. Countable means either finite or denumerable. Now to consider A and B is the denumerable sets. The previous theorem, you have to be proceed the steps. We get that A union B is also denumerable. Hence A union B is countable. Next to go for the one more very important interval, that prove that 0 1 is uncountable. Prove that this 0 1 is uncountable. By contradiction we can take suppose 0 1 is countable, then there is a bijection F from n to I, n to 0 1 defined by F of n equal to An for every n belongs to n, where An is in the form of decimal and it belongs to 0 1. It belongs to 0 1 means the initial point is 0, final point is 1. In between 0 1 there are so many subintervals, say 0 A1, if it is end with A1 it start with A1 A2, if it is end with A2 start with A2 A3 and so on. That means the last element first element, last element first element, last element first element coincident. What it shows, if they are like to be coincide, F does not becomes onto, which is contradiction that F is bisective. Therefore, our contradiction, that means our supposition what you taken 0 1 is uncountable is wrong. Therefore, 0 1 countable is wrong. Therefore, it should be 0 1 is uncountable. After this, you have to take some exercise. These examples to try yourself. Prove that the set of prime numbers is countable, and if B is countable, F from A to B is injective, then A is countable. Prove that every subset of integers z is countable. Prove that the set of positive rational numbers is countable. You have to be try to work out examples on this one. And the one more example after this I did for the references. You have to refer this theorem. What are the reference I taken here? These are the reference I taken. Thank you.
For that you have to connect it to the queue.